Jai Hind to all. My name is Dhanshri Parihar, Assistant Professor, Department of Computer Science and Engineering, Ajay Kumar Garg, Engineering College. And today my topic for discussion is Arithmetic and Logical Unit. And the topic is multiplication algorithm from the subject Computer Organization and Architecture. So the content of this PPT will include binary multiplication, which is further divided into two parts, that is the Booth multiplication algorithm and the EAQ algorithm. And then we have sign magnitude multiplication, then we have division algorithm and the look ahead carry adder. Now what is binary multiplication? As we can see in this diagram, we are just performing a binary multiplication between two numbers, that is 23 and 19. The binary equivalent of 23 is 10111 and 10011. So while performing the multiplication operation, we are just adding the two bits when we are multiplying the two binary numbers. Like in a first step, when we are multiplying 1 with the 1, so 1 of 1 is, the ending operation of 1 and 1 is 1. Then this 1 is multiplied by this one, again ending of 1 and 1 is 1. Then 1 with 1, 1 with 0 is 0 and 1 with 1. So the first, that is the binary equivalent of 23 is known as multiplicand, the upper number, and the lower number from which we are multiplying the upper number is known as multiplier. So why we are considering this name and focusing on it as while performing the algorithmic multiplication, these names are very important, and we are using some abbreviations to denote this multiplicand and multiplier in our algorithm. Now the intermediate results like this are known as partial products. Okay, and the end result is our product, but that is 437. So the sign of product from the sign of the multiplicand and multiplier is same, that is positive. It may be positive or it may be negative. That will depend upon your multiplier or multiplicand. If both are negative, then it is a positive number. If any one out of them is a negative, then the answer will result in a negative number. Now let us start with how this kind of multiplication is being performed by a computer system. For doing such operation in our computer system, we need certain algorithms, and for performing a sign magnitude multiplication, we will need a sign magnitude multiplication algorithm, which is also known as EAQ algorithm in short language. So what is this algorithm is all about? As we have taken the example of this multiplying 23 with 19, we will be considering the same example for performing this algorithm. For understanding this algorithm in a better way, there is one way of representing this algorithmic step in a form of a flow chart. So let us have a look at this flow chart, how the functioning and the workflow will occur in this algorithm. So the very first step is to perform the multiplication operation that is defined in our this rectangle, and then we have a multiplicand and multiplier. So we have 23 and 19 multiplied by each other, where we are taking 23 to be multiplicand and 19 to be multiplier. So this multiplicand will be denoted by the variable b. So we are taking this variable b to holding the value of multiplicand, and the multiplier will be represented by the variable q, which is used for holding the binary bits of this multiplier. Okay, that is the number 19, the binary equivalent of number 19. So this is the very first step, initializing the variable to hold the values of your multiplicand and multiplier bits. The next step is to perform a check for this QS bit. Now what is the QS bit? In a case of this multiplier, as we know that the binary equivalent of 19 is 10011. Okay, what we are doing? We are just multiplying 10111 with 10 So what we are doing, 1 0 1 0 triple 1 is multiplied with 1 0 0 1 1. So this is the binary equivalent of 23 and this is the binary equivalent of 19. So here this value is being held in Q. Now what is this Q of S, or we can say Q of N over here in the second step? The least significant bit of multiplier, that is this 1 0 0 1 1, that is 19. So the LSB is this bit and MSB is this bit, the first bit. So the least significant bit of the multiplier, that is the 19, which is held in the variable Q, will be used for performing a lookup operation. Okay, that is our Q of S, or we can say not Q of S but Q of N. And what is Q of N? Q of S is the sign bit, the most significant bit. So this Q of S is the sign bit, that is the most significant bit of our multiplier variable, we can say, which will be holded in the variable Q. And Q of N is the least significant bit of that multiplier Q. Now what we have to do, we have to perform a lookup. Whatever be the sign bit for this Q, that will be the part of your the sign bit of A. A is our accumulator, okay, which is initially holding the 0 value in it. E is a flip-flop which is holding only a 1 binary bit. Later on it is used as to hold the carry bit generated from an addition between the multiplier and the accumulator, okay, which we will be seeing in our algorithm how its value will be affected when a carry bit will be generated after performing the addition operation. Now SE is representing the sequence counter that is used to maintain the sequence of the number of steps available in your algorithm. So for holding those value, we will be using SC. Qn is that I told you, this is your Q of N, and complete value is Q, that is the least significant bit of the multiplier. And when we will perform a lookup, whether it is the value is equals to 1 or 0. If it is equals to 1, then we have to perform this operation, that we have to add the accumulator content with the multiplier content, and the resultant will be the new updated value of your accumulator along with the E flip-flop carry bit. So whatever the carry will be generated will be put in the E value, it will be updated. If it is 0, it will not be updated, it will remain 0. And if it will be 1, the value of E will be updated. That we will be going to see soon in our algorithm. And after this, we have to, if it is 1, we have to perform this addition operation between accumulator and the multiplier bits. And then we have to perform shift right operation between the E bits, accumulator bits and the multiplier bit Q. And after performing that right shift operation, moving the bits one by one toward the right hand side once, and then we have to decrement the sequence counter by 1 so as to move towards the next step. And till we have to proceed this step till we will reach the value of sequence counter to be 0. Suppose we are having the 5, the value of SC is 5, then we have to perform it till we will reach 0, that is 5 times. And at the 6th iteration 0, we will be stopping our algorithm and we will be obtaining our result. So need to control when to stop our algorithm and when we are getting our result, in which step we need this sequence counter. So these steps we are following, and when the Q of N is 0, we will be directly performing this shift operation on the flip-flop E, the accumulator A and the multiplier bits Q. So by using this flow chart, let us have a look upon the example how we will be performing this EAQ multiplication. This is the example which has already been done. We will be doing the same example. So let us consider how to formulate the algorithmic table. So let us start with the values what we have to put in our table. Very first value is our multiplicand bit. That is B. Variable B is used to hold multiplicand. Then we have E. E is our flip-flop. Then we have A that is accumulator bits. Then we have Q. Q is the multiplier bits. We will be taking this column to be somewhat little bit extended because the value of this Q is in terms of 5 bits. A is also somewhat extended, so we will be taking it also. The column size will be somewhat, I can say I need to extend it so that it can accommodate 5 bits inside it. Now next is the sequence counter. Okay, the last one bit. So what is E? A is accumulator, E is our flip-flop holding only 1 bit inside it, and A is accumulator holding the number of bits similar to the number of bits which are present in our multiplier bit. So here Q is the multiplier which will be holding the value 19, and the binary equivalent of 19 is 10011, and the sequence counter. So what will be the value which will be holded inside the sequence counter? It will be totally depend upon the number of bits, the size, the number of bits inside your this multiplier bit. So here we are having 1, 2, 3, 4, 5 bit. So the sequence counter will be started from binary 5. You can also write it like this, 101. Because computer is not able to understand 5, we need to convert it into binary. 101 will be the value holded inside our sequence counter. And what should be inside A? Initially, as we have, if we perform a lookup in our this flow chart, initially it must be 0, and the this flip flop will also be 0. So here we will be putting zeros. But how many zeros we need to put? So the dependency of number of bits in accumulator is totally upon the multiplier bits. Here we are having 5 bits in our multiplier. So the same number of bits will be available in our accumulator. So again we are having zeros, but how many zeros? 5 zeros. 2, 3, 4, 5. So dependency is totally upon the number of bits available in our multiplier in this algorithm. Now next, as since it is a flip-flop, it will be holding only one binary bit. Initially it will be 0. And what we need to put in multiplicand? The multiplicand is the number 23, that is 10111. As we are taking this column to do our operations, we will just writing that 10111 is our multiplicand, and we will be using it for performing operations also. So, or we can say operations details, we can say we are writing over here operation details. So that is the way how we can start our algorithm, and by following that flow chart, that is a simpler way of maintaining this algorithm. So very first step is we have done, we met with. Very first step is for multiplication, we are taking it to be variable b, and then we are taking q to be a multiplier, that is 19 and 23, and then initializing all the variables, a to be 0, e to be 0, and then q to be the value of 19 in it, and b the value 29 in it, 23 in it, the binary equivalent of that. Now the second step is to perform a check on q of n. So looking here, what is q of n? And I told you earlier, this q of n is the least significant bit of our multiplier, that is 1. So I am writing over here what is q of 1 in very first step, 1, which we have taken from this bit. This is our q of n. So we have taken this to be 1, and what will happen if the value of qn is equals to 1? We have to perform an addition operation between accumulator and the multiplier. Okay, and then the result will be followed in forming the new value in the accumulator, and then the carry bit will be passed to the flip-flop E. Okay, so what we will do now, EA, it will be like this, EA equals to A plus B. So this operation need to be performed. Here, this is Q, this is A, and this is your B. So here we are writing this 10111, that is the value of B. Okay, and what we are doing, we are multiplying 23 into 19. Okay, 23 is equals to 10111, and 19 is equals to 10011. This is our B and this is our Q. So after performing addition, what we will get? 1 1 1 0, binary addition, this. Okay, and the next step is to perform the shift operation. Shift operation, by doing this we have to perform a shift operation. Shift operation between E, A and Q. Okay, here the value of E will be same because there will be no carry bit in the last bit. Here we do not have any carry generation. 0 plus 1 is 1. If we will get an extra bit, then we will move that bit toward our E and it will be holded by A and cannot be vanished. Okay, next is to perform SHR, shift right operation between E, A and Q. So what we will do, we will be moving this 0 over here, this 1 over here, this 0 over here, this 1 over here and this 1 over here, and this 1 will be moving towards your Q. This 1 will come over here, this 1 will come over here, this 0 will come over here, this 1 will come over here, and the last one will be got vanished, and we are not taking it as it will be removed from our multiplier during our shift operation. So this result we are getting now. Okay, now next is to decrease our sequence counter to by value 1, SC equals to SC minus 1. So it will become 4 now. That is the next, after doing this shift operation, we will be doing this. SC equals to SC minus 1. Now, so we will be proceeding towards our, whenever our sequence counter will get decremented, we will be moving towards our new value. Now, next again, we need to check the Q of n bit. And after performing this shift operation, what is the least significant bit value over here? That is 1. So Qn again is 1. And what we have to perform? We have to perform again EA equals to A plus B. Now we have to take the updated value of this A, which we have taken in the previous step after performing addition and then the shift operation. So updated value of A is 0 1 0 1 1. Okay. Now we have to perform addition with our this binary B. It will be like this, A plus B. Okay, this is the new updated value of A after performing the shift operation, and the value of B is already, we know that 1 0 1 1 1 0 1 1 1. Now perform addition. What we will be getting? 1 plus 1 is 0 1, 1 1 is 1 1, 1 1 is 0 1, and 1 1 is again 0 1, and 1 1 is again 0 and 1. So where we will be putting that 1? Inside your E operation. So this 0 will be replaced by this 1. That is a carry bit generated during performing our addition between our accumulator and our multiplier bit. So in this algorithm, whatever carry will be generated, that cannot be discarded, that will be holded by our flip-flop E. Now the value of E will be updated, and the previous value of Q is 1 1 0 0 1. Now the next step is to perform the shift operation again, SHR between E, A, Q. So when performing shift right operation, we will be moving each and every bit toward right hand side. Okay. So here we will left with 0, then we have 1, 0, 0, 0, and then 1. This 0 will be gone here, 0, 1, 1, 0, 0, 1, 2, 3, 4, 5, and this one got vanished now. Okay, so we will be left with this result during step number 2, that is 1 0 0 1 and 0 1 1 0 0 in A and Q variable, that is in accumulator and in a multiplier bit. Now next again we have to reduce the sequence counter by value 1. Till what we have to follow this step? Till we met the sequence counter to be 0. Okay, and when we are getting sequence counter to be 0, at that end of that step, we'll be getting our answer. That is the multiplication of 23 and 19. Okay. Now next is sequence counter will become 3. 4 minus 1 is 3. And now again we will be performing a lookup for Qn equal value. So Qn is the least significant bit of this multiplier again, but now in this case it will become 0. And whenever the Qn value is 0, as we can see over here, whenever it is 0, that this Qn, then whenever it is 0, then we have to perform the shift operation directly. There is no need of performing your addition operation. This operation is saying, this step is saying this directly, that we have to shift E and Q and then decrement the sequence counter. There is no need for performing addition operation. So what we will do, Qn is now 0. We have to directly perform shift right operation between E, A and Q. Okay, so E, that is flip flop, accumulator and Q. So directly perform the shift operation. This 0 will be coming here and 1 will be moving here. Then 0, 0, 0. This 1 will be moving here. This 1. And then we have 0, 1, 1, 0. This is the result we are left with. And what about this E? A 0 will be inserted over here because no addition operation is performed and we do not get any carry bit over here. So we will be putting 0 over here. Now after performing this step, again we have to decrement the counter by 1. It will become 2. Okay, for 2, let us do step number 2 in another column because I am out of the space right now. So I will be erasing the previous column and taking the latest one. This column I am erasing so that to reusing this column again. Because we are left with 2 more steps right now. And we are right now at step number 2. So I will be performing step number 2 over here. When the value of Qn is equals to, that will be checked. Let us draw this line and then again this line. Okay, so when SC equals to 2. So when SC equals to 2, again we have to perform a lookup for the Qn bit. So the Qn bit over here is 0 again. Okay, again we have to perform shift right operation between E, A and Q. E, that is the flip flop, A accumulator and the multiplier. So let us perform that shift operation. What we will left with, here we are having 0, then we have 0, 0, 1, double zeros and 5 bits, and 1 0 is proceeding over here, 1 0 and double 1, like this. Okay, there is no need of performing addition again because we have the value of Qn to be 0. That the least significant bit of multiplier is 0 and then only the shift operation. After this, we have to perform our decrement operation and we will be reaching sequence counter to be 1. Sequence counter is decremented by 1 and again we have to perform the check for the Qn value, and the Qn in this case is right, it is 1 now, and whenever the value of Qn is 1, what we have to do, we have to perform an addition operation and to generate the new value of EA, that is A plus B. Okay, what is the value of A? Let us 0 0 1 0 0 and we have to plus it with this B, 1 0 1 1, and what will be the answer? 1 1 0, again 1 1 and 1. This is the answer. So this is the result of this addition, and we do not generate here any carry bit because 0 plus 1 is 1. So the value of this E is 0, not 1, but it is 0 because no carry bit is there, and 0, 1, 0, 1, 1 that we have copied from the above, and we need to perform now shift operation. Let us extend this column for performing the shift operation. So S, H, R, E, A and Q between these three. So when moving this 0 over here, what we will left with 0? Here this 1 will become 0, this 1 will move over here, 1, 0 and 1. Okay, and further this 1 will be moving over here, then 0, 1 and 0 and 1. 1, 2, 3, 4, 5 for sequence counter 1. So updated value of Q will be 1, 0, 1, 0, 1 and 0, 1, 1, 0, 1. Now for sequence counter 0, decrementing sequence counter 1, now we will be reaching the last step where we are getting our solution, that is the multiplication result. Let us again perform the check. Here the Q of n is equal to 1. Again we have to perform EA is equals to this A plus B. A equals to A plus B, and then after that we have to perform shift right operation between E, A and Q. So let us have a look. The updated value for A is, this is 0, 1, 1, 0, 1. Okay, what we have to add in this B, 1, 0, 1, 1, 1. So add this, 1 plus 1 is 0, 1 plus 1 is 0, and this is again 1, 1, 0, 1, triple 1, 1, 1, double 1, 0, 1 and 1, 1, again 0, and we have a carry bit over here also. And then I will be copying this like this. Okay, and then performing the shift operation between A and this A and this is B. So whenever performing shift, this 1 will be moved toward this 0. Here it will be 0, then 1, then 0, 0, 1, 0, and then this 0 will be moved over here, 0, 1, 0, 1 and 0. This 0 will be moved over here, 1, 0, 1 and 0. So this is the final value of our this A and Q, and this will be our result. So let us check whether we will met our result or not. 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, and then we have this 1, 0, 1, 0, 1 to be the end result. 0, 1, 1, 0, 1 and 1, 1. So at the end in A and Q, whatever value will be coming in your this A and Q, that will be your final result. That is the binary equivalent of the number which is obtained after the multiplication of this, that is 437. Okay, so whenever you are performing this algorithm, whatever will be result coming in your sequence counter 0 at the end, that will be your binary equivalent of the number which is being. So A and Q is holding the end result. Okay, this is all about this algorithm. Now next, this is the block diagram of this algorithm. So thank you so much.